Can you hear me?
Okay, so our next speaker is Artem Lopatin from the University of Campinas in Brazil, and they're going to speak about invariants for simple evolution algebras. So over to you, Artem.
So you can see my slides, yes?
Yes, that's
Okay,
clear. Thank you.
thanks a lot for the introduction, and thanks a lot for organizers for giving me opportunity to give here a talk. So today I will talk about invariants for some algebras. Yes, in particular I will talk about evolution algebras, but I will not only talk about evolution algebras, I will talk in a more general setup. But before considering algebras, I would like to give two very simple examples of algebras of invariants. So what are invariants? Invariants, it's something very simple. So we have, let's say, ring, polynomial ring, usual one, and we have symmetric group, which acts by the permutation of variables. So we can permute variables, and those polynomials, which are fixed with respect to any permutation, they are called invariants. Of course, in this case, in this particular case, invariants are symmetric polynomials. So this case is very well known. We know generators, which are elementary symmetric functions. We know that this algebra is isomorphic to polynomial algebra in new variables. So it is very trivial, classical example. Let me consider another easy example, but maybe not so trivial. So here we have polynomial ring in three variables, and instead of all permutation as it was before, we'll consider only cyclic subgroup. So we will consider only two non-trivial permutations, this one and its square. And so this cyclic subgroup is generated by this permutation, which is cycle. And so we can consider invariance with respect to this action of this new group over a polynomial ring. So here, invariants are again those polynomials which are fixed with respect to this action, and it is not hard to see that here we have four generators. So we have the same generators as it was before, elementary symmetric polynomials, together with a new one. So this new generator, as anyone can see, is not symmetric polynomial. So it is something new. And of course, we can generalize the situation, and instead of group G, which has been considered before, we can consider actually any subgroup of a general linear group, and then we have its action over x1, x2, xn, etc. And so we'll get some algebra of invariants. So what I'm going to do now. Today, I'm going to talk about actually, it's a project which started some years ago with me and Maria Alejandra Alvarez, and second part I was doing with Kaygorodov, and today I will talk about third part. So what do we have here? We have some field F, which we usually assume to be algebraically closed, and we consider that characteristic can be positive as well. So here I would like to make a remark that today normally we'll talk about the case of zero characteristic, but of course all this can be considered in case of arbitrary characteristic as well. So here we consider a dimensional algebra A, so it is important that the dimension of this algebra is finite, and of course here we have this non-associative conference, so algebra A can be non-associative. So it is just a vector space endowed with some bilinear multiplications, that's it. So we consider some subgroup G, which lies in the group of all automorphism of algebra A. So here, what for we need structure of algebra A, what for we need multiplication algebra A to define the group of all automorphism. And so we consider our group as a group in this group of automorphism. And actually, today in my talk, I will always assume here the equality, that group G is actually equal to the group of automorphism. But in the definitions, we can consider some subgroups, so I will keep the situation a little bit more general. So then we would like to make our life a little bit more complicated. So instead of one algebra A, we consider direct sum of m copies of this algebra A. And so the group G acts on this direct sum diagonally. So it's explicitly written here. What exactly does it mean? And then we can consider coordinate ring of AM. In other words, it's just polynomial ring, which is written here in variables which have indices R and I, so X, R, I are variables, and we just consider all polynomials in these variables. So here, index R, it's a number of algebra, which we consider, so it ranges from 1 to n, and I is a number of basis element to which these elements refers to. More explicitly, I will explain it right now. So to define these X, R, I as functions, first of all, we are going to fix some basis of algebra A, and so we fix it, and we use this notation for i's coordinate. And then we can consider this function X, R, I as a function over direct sum of m copies of algebra A as written here, and so then any element of coordinate ring is, of course, just a polynomial function. It's important that we can consider it as a function. So we have the action of G on AM. In the usual way, it induces the action on the coordinate ring. Explicitly, it's written here. And finally, we obtain the definition of our algebra of invariants. So it consists of those elements from coordinate ring, which are fixed by the action of the whole group G. So here we have action of G over coordinate ring. If for some reason we would like to get we don't want to consider this action, just the action of group G over algebra A, we can consider another equivalent definition. This equivalent definition works in case the field F is infinite. And so here I will always assume that the field F is infinite. So in this case, we can say that algebra of invariants consists of those polynomials which have one and the same value over each orbit, so over any point of each orbit. So what explicitly does it mean? We can pick up some orbit, G orbit over AM, and then in any point of this orbit, this polynomial F should have one and the same value. So in other words, we can define polynomial F over orbits, over sets over orbits. And so this is actually key motivation for consideration of algebras of invariants. It's a basic fact that algebra of invariants can be used to separate closed in Zariski topology orbits. So invariants can be used to treat some classification problem, to try to classify orbits of the action. It's key motivation of consideration of such invariants. Invariants have a lot of applications. I will not talk much about it. For example, recently, some people like Ben Bloom-Smith, and together with his multiple courses, he's working on applications of invariance theory to machine learning. And of course, there are many other applications to real life, like to differential equations, for example, to classification of differential equations. But today I will not talk about applications. I will just concentrate on this particular problem. So what problem do we have here? So now, from now on, this group is just group of automorphism. And to shorten the notation, we'll use this notation. So we write down I am A, so it means that we consider algebra of invariants of algebra A, where we consider m copies of algebra A. So here m can be actually arbitrary. We'll try always work with arbitrary m, not just with m equal to 1. So what is advantage and of this construction? So why we are so interested in the structure of algebra here? Motivation here is the following one. So when algebra of invariants is given like this, then we can always construct some invariants just because of the fact that we have here algebra A. I will talk about it. Actually, it's written here. And another interesting motivation is the following one. One of the ways to consider groups is as groups of automorphism of some algebra. So roughly speaking, any simple group can be given as a group of automorphism of some simple algebra. And there is a list of statements of this kind, and so this kind of presentations of group is quite interesting one, and so it's the second motivation of consideration for this algebra of invariants. And so, as I said, here we can construct some invariants, so let us do it. So first of all, we consider some element A from algebra A, and we denote by LA and RA two operators of the left and of the right multiplication by element A. So LA and RA are, of course, operators, linear operators. So when the basis is fixed, we can consider them as matrices. So they have traces. So we can consider a trace of LA. And now we are going to consider trace, but not as a trace of operator, but as a function. So here's the trace with index L is a function from the algebra A to the field F, which is given by this equality. So here I would like to state that the basis is fixed. So here everything is fine. Well, of course, this construction doesn't depend on the choice of the basis. And so this map, as anyone can see, is of course linear. So then this trace we can consider as an element of the coordinate ring of algebra A. So actually it's a homogeneous polynomial of degree 1 in variables of coordinate ring. Exactly in the same way, we can define the trace of the right multiplication, or simply speaking, the right trace. So we have left trace and left trace and right trace. So as I said, both of them belong to the coordinate ring, and moreover, it can be relatively easy verified that both of them are invariant with respect to the action of group of automorphism. So both of them actually belong to this algebra of invariants. But just to these traces, of course, for us is not enough. So what we can do? Here, instead of considering just one operator of the left or right multiplication, we can consider several operators of the left or right multiplication by elements of algebra A, and consider composition of these operators and take trace of this composition. But and doing this, we can define a map now from AM to F, and so then we will define a multilinear element of the coordinate ring. And this element is called operator trace. It's called operator trace. Later, I will give explicit definition of this construction. Actually, what I said, it's not actually enough. We can generate even more operator traces. And so all these operator traces are invariants, and we can define subalgebra of algebra of invariants, which is generated by operator traces like this. So it's subalgebra, which is generated by all operator traces. Every time to say operator trace is quite long, so probably I will just call them traces. So we can say that this algebra is generated by all traces. And then we say that for algebra A and index M, we have Artem Procesi Iltyakov equality, or in a short form, we call it AP equality, if and only if algebra of invariants is exactly equal to its subalgebra generated by all traces. And in many classical situations, we actually have this equality. So here I would like to make the following remark. So of course, since here we only consider traces, so then this equality normally refers to the case of zero characteristic. Yes, sometimes it holds in case of positive characteristic, but it doesn't really have to hold in case of positive characteristic. To treat positive characteristic, here instead of just one trace, we have considered other coefficients of characteristic polynomial. So here we can take, let's say, determinant, and we can take other coefficients of characteristic polynomial of square matrix, which are between trace and determinant. In this case, yes, we can formulate some analog for this equality and to study this analog. But here we are not doing it, we just work with traces. Okay, and so after this definition, I would like to consider cases which are classical cases, which are very known cases where this API equality holds. The most classical cases, of course, are the case of n by n matrices. So we have several n by m matrices. So here I would like to repeat that we have this index m, and so we do not work with just one algebra, we work with several copies of this algebra. And so in this case, everything is generated by traces if characteristic is 0 or if characteristic is greater than n. Well, in this case, if characteristic is greater than n, then all coefficients of characteristic polynomials, they can be obtained using traces. That is why this result also holds in case of characteristic greater than n. These are very classical results. They goes back to Sibirskii, to Procesi, and to Artem, who conjectured this result. In case of Octonian algebra, so Octonian algebra is a free or is a simple alternative algebra. And in case characteristic is different from 2, in this case, API equality also holds. If characteristic is equal to 2, then we don't know what are generators for the algebra of invariants in case of Octonian algebra. We can also consider split Albert algebra, so it's exceptional simple Jordan algebra. And in this case, if characteristic is 0 and we have just one algebra or two copies of algebra, then API equality also holds. In this case, what happens when m is greater than 2 here, it's an open problem, we don't know this. So in all these classical examples, we have one in common, algebra, which we consider is simple. Actually, we can also consider Jordan algebras and something known about Jordan algebras, simple Jordan algebras, of course, we can consider simple Lie algebras, but here I will not talk about these results. So actually, in many cases, this equality is known to be 0. And so what we are going to do here, from an abstract, as you can see, here we will concentrate on a special case when we deal with evolution algebras and, of course, simple evolution algebras, and we will restrict ourselves to the case of dimension 3. But before this, I will formulate some other results which were obtained some time ago. They are relatively new because they not printed yet. They are not yet accepted to journal, but you can find them in archive. So I will start with the case of two-dimensional algebras. And actually, this API equality, I will already formulate the main results about two-dimensional algebra. This API equality holds for simple two-dimensional algebras in case characteristic 0, and in case group of automorphism of this algebra is not trivial. This remark about group of automorphism is not trivial is very important because there is classical example by Vladimir Popov at the end of last century. He obtained this example of a simple algebra which has trivial group of automorphism, and its algebra of invariants is not generated by traces. But you see, if we have a trivial group of automorphism, then algebra of invariants is just coordinate ring. And we probably not very interested in generators because it's just generated by variables. It's just polynomial ring, we know it's generators. And so the fact that it's not generated by traces, maybe it's not very important. So here we may formulate like a very general conjecture, which I don't claim it's true, maybe it's true and maybe it's not true, and it's the following one. We have finite dimensional algebra, we have characteristic 0, this algebra has a non-trivial group of automorphism, and then API equality holds. Another way, then algebra of invariants is just generated by traces, but it's extremely general conjecture, so probably it's not true. Okay, so some notations. Okay, so here we can consider this tensor product and elements and consider this element from this tensor product. So this element is called generic element. Why we need generic element? Because we would like to write down explicit formula how group G acts on the coordinate ring. And so this formula is written here. So here on the left, we have an element of this algebra, and on the right as well. So it's just equality. It's just a good formula which can be easily used. And so here we start with maybe the most difficult part, which is explicit definition of trace operator. And so we have these two easy definitions, and we would like to obtain general definition. So how it works? We start with the absolutely free unital algebra in this lattice. So here letter, I will refer to this lattice as x0, x1, but I guess this lattice are rather chi. I don't know how to pronounce them. It's Greek lattice. So here letter x0 will play at some technical part. So to a certain extent, maybe it's not very important as the rest of the lattice. And so we take some element from here, and first of all, we are going to define substitution. Substitution is defined in the usual way, substitution in a polynomial. And then we would like to define operators of the left and right multiplication by h, where h is, again, a polynomial from this ring. So they define in the usual way. And then we use this notation, so we can, if letter P is from the set of two letters L or R, then like this and like this, we will define operators of the left and right multiplication. So here is operator from the left or right multiplication by element A, and here it's operator of left or right multiplication by some polynomial. And so here's the definition. So we take a homogeneous element, which is homogeneous of degree 1 in x0. So as I said, this variable x0 is a little bit technical variable, and so we need this technical condition. And so it means that each monomial of h contains this letter just once, exactly one time. And then for every a from direct sum of m copies of a, we can define linear operator, this linear operator, by this equality. So here we put b instead of first element. And then we can take a trace. So we have a linear operator, and we can take trace of this linear operator. And so here's the definition. So here's the definition. So for example, when we have our polynomial just x0, then it will be identical operator here, and trace is just equal to n, where n is dimension of algebra. So here is left trace and right trace. So here you see that roughly speaking, we can say that like degree here is 2, but actually we don't pay attention when we deal with degree, for example, to x0. And so then here we have degree 1 here as well. So we use this notation because it's more convenient for the matter of convenience. Okay, and so here's a list of some properties. First of all, exactly in the same case when we were considered the left and right traces, we can verify that this operator trace is an element of coordinate ring. Simply, we can also verify that it's invariant. Well, actually, here we need some proof. It's not so straightforward. And about multi-degree. So if H has this multi-degree, so I would like to repeat that degree with respect to the first coordinate is always 1, then trace of H has multi-degree like this. So as I said, when we consider multi-degree, we don't pay attention to x0. And so now we can define this algebra, which is generated by all operator traces, and together with 1, of course. And so now we have explicit formulation of API equality. Okay, so now I would like very briefly to consider the case of algebras of dimension 2. I will not consider all the details. First of all, here we work in case of algebraic closed field. So in this case, we have classification of algebras of dimension 2. Talking about classification, it's always important to keep in mind that normally the can be several classifications, and so it's quite important to choose the one which better suits our needs. So here we use this one, which was done in 2019 by Ivan Kaygorodov and Yuri Volkov. So this classifications, it's quite popular. It has a lot of references to it, so we are going to use it. So here is a notation of an algebra. In brackets are parameters. Parameters are from field, and sometimes there are some additional restrictions on the parameters. Here, as I said, I will not consider all the details. So here is a table of multiplication. So an element, let's say in position 1, 2, it means it's a product of first and second basic vectors. So basic vectors here, E1 and E2. So here is a product of it. And in the last column are written automorphisms of this algebra which are not trivial. So all automorphisms which are not trivial. So sometimes automorphism may depend on some letter. Then of course we always assume that the determinant of this matrix is not 0. And so here this classification goes on. So here sometimes these algebras they depend on 4 parameters. So our first step was classify all simple two-dimensional algebras. It turns out it has not been done before for some reason. So we've got this classification, and then we've got some quite funny corollary. I mean, I was quite surprised when I got it. So automorphism group of any two-dimensional simple algebra is finite. I don't know why, but I don't know, can this be proven using some general methods without using classification? But okay, we have this side result. And then we, in case of characteristic 0, we explicitly described all generators for all algebras of invariants. So here we consider, of course, the case when a group of automorphism is not trivial. So if group of automorphism is trivial, then algebra of invariants is just coordinate ring and we have nothing to do. Otherwise, we present here a complete list of algebras with non-trivial group of automorphism and generators of algebras of invariants. So this case is the most difficult one, as you can see, because here we have more complicated invariants. So, and then as corollary, we obtain this API. Equality holds for simple two-dimensional algebras with non-trivial automorphism group. And we've got another interesting corollary. So if we have two-dimensional simple algebra, yes, two-dimensional simple algebra, then it always admits a symmetric invariant non-degenerate bilinear form. So here invariant means it's invariant with respect to the actional group of automorphism. Symmetric and non-degenerate means as it usually means. So this connection between simplicity of algebras and the presence of some bilinear form, I think it's quite interesting. For example, in case of Lie algebras, we can take Killing form, and if algebra is simple, then this Killing form, it's also non-degenerate, it's always symmetric, it's always bilinear, and it's always invariant as well. So this connection probably can be studied more deeply. Okay. So the second part is about Leibniz algebra. So here's the definition of Leibniz algebras. So key example of Leibniz algebras is of course a Lie algebra. So because Lie algebras are important without any connection with Leibniz algebras, so it's reasonable to consider Leibniz algebras which are non-Lie algebras and Lie algebras separately. So here we will concentrate on Leibniz algebras which are not Lie algebras. So here we have ideal denoted by Leib L, which is sum of squares of all elements. It's always ideal, and in case L, algebra L is not Lie algebra, then this ideal is non-zero. So this simple fact implies that there is no simple Leibniz algebras which are not Lie algebras. So in theory of Leibniz algebras, of course, people would like to work with simple Leibniz algebras, and so they change slightly definition of simplicity, and they refer to Leibniz algebra to be simple when this ideal is the only non-trivial ideal. So here I'm again talk about non-Leibniz algebras. And so denote by this symbol the family of all three-dimensional non-Leibniz algebras over the field of complex numbers. And so here we need, as before, classification result. With classification results, here quite different and difficult situation. Well, first classification was obtained here with some misprints. So it was pointed out in these two papers. So paper A and B, they both are exclusively dedicated to classification of these three-dimensional Leibniz algebras. They use different methods. So in the second paper and paper B, computers were extensively used. So essentially speaking, some algorithm was considered which helped to classify. And so here, some not computer-based method was offered. And so in both of these papers, it was written that this paper C contains some inconsistencies. But then again, it turns out in paper A, there are some problems as well. So classification given here is not complete. In our paper with Ivan Kaygorodov, we finished sort of this classification and proved that this our classification is equivalent to this classification. Equivalent here means we explicitly for each algebra from one classification showed a change over the basis to obtain some algebra from another classification. So here it should be pointed out, so if we have two classifications of some algebras, then normally it's very hard to establish that they're actually equivalent. Here by establish, I mean explicitly establish by presenting base changes of the basis, because to find out what change of basis we have to do, we actually have to solve some system of equations which are not linear, which are square equations, and in many cases it's hard to do. So anyway, we have some classification of over complex numbers of three-dimensional Leibniz algebras, and so we apply this classification to obtain our results. So I will not give here explicit formulation because it will take some time. So I will just mention that we explicitly described all generators for all algebras, for all Leibniz algebras here over complex numbers. As about API conjecture, here situation is the following one. As I said before, none of these algebras are simple. So we don't expect that this API conjecture should hold. So sometimes it holds, sometimes it doesn't hold. And as corollary, we obtain the following result. So if we have two non-nilpotent Leibniz algebras, which are not Lie algebras, then they can be distinguished by means of all traces of degree less or equal to 2 and dimensions of its group of automorphism. So what is the motivation of this corollary? As I said before, so when we deal with algebras, one thing is that we have classification, but another problem is if we have some particular algebra, to determine to which algebra it corresponds in some classification. So this problem can be quite difficult one. And so all methods which can help to show that two algebras they actually isomorphic, this kind of results they're quite important one. And so some people, for example, there is result over Jordan algebras of dimension 2, but here's the case of positive characteristics should be considered. So there is a result that in this case polynomial invariants polynomial identities can be used to distinguish all such journal algebras. And there are some other results in these directions where people use polynomial identities. Here we use invariants to distinguish algebras. Okay, so now the case of evolution algebras. Evolution algebras, they were considered, they were introduced several years ago, actually already quite a lot of years ago. And motivation for this algebras is, of course, to apply to some evolution problems, some problems concerning with genetics. So definition, but apart from these applications, these algebras are quite interesting. They have a very nice combinatorial structure on one hand, and on the other hand, there are a lot of them. So this class of algebras contains a lot of algebras. But it also should be pointed out that it's not variety. So subalgebra of evolution algebra doesn't have to be evolution algebra. And so here's the definition. So we have arbitrary field F. So here I will consider only the case of finite dimension, but the case of infinite dimension is also can be considered. So algebra is called evolution if its tableau of multiplication is diagonal one. So what does it mean? It means that there is some basis. It's called natural basis, such that product of two elements with different indices is always 0. So if you consider table of multiplication of this algebra, then it is diagonal. So let me come back to, let's say, to two-dimensional case where we have tables of multiplications. And yeah, here, let me see, is any algebra from this list? No. Okay. No. So here, of course, there are two-dimensional evolution algebras, but in this basis, none of these tables of multiplication is diagonal. Okay, no, this one. No, here's 0. It cannot be 0. So anyway, this table of multiplication of evolution algebra should be diagonal with respect to some particular basis, not with, of course, not with respect to any basis. And so this particular basis is called natural basis. And so here we introduce some notations. We introduce so-called structure matrix, which is very important. Another important definition of algebra A to be regular. Actually, regular algebras, they are studied not only they are itself very interesting object, and there are some papers about regular perfect algebras. I will use the word perfect. And so it's the algebra such that square of this algebra is equal to algebra A. In case of evolution algebra, when it's perfect, it has some additional and combinatorial properties. So here, let me define graph. So when we have evolution algebra, we consider some natural basis, and we take elements of this basis as vertices of a graph, and then we write down an arrow if from I to j, if we consider basic element ei, we consider square of this element. And so if square of this element contains with non-zero coefficient j, then we have an arrow from I to j. So here we have arrow from I to j in case this coefficient is not 0. What is this coefficient? It's exactly the coefficient of ej in a square of ei. So we consider this graph. A simple remark, of course, it doesn't have double arrows, but it may have loops. Okay. And so here's some list of facts, quite known ones from, from some published papers about evolution algebras. So here we consider some natural basis. So if algebra is perfect, then the determinant of structural matrix is non-zero. So if and only if, so it's a criterion when algebra is perfect. Algebra A is simple if and only if it is perfect and this graph is strongly connected. So here already we can see that this graph is extremely important, and we have actually a criterion how we can verify that algebra is simple. And for our purposes, we are going to consider simple evolution algebra. So this fact is extremely important. Another fact that algebra is indecomposable. The definition is written here, even only if the graph is connected for every natural basis. And finally, property D shows that actually, in case of perfect algebra, this graph is unique. So if so, we have here evolution algebra A, and if we have additional algebra A prime, which is also, of course, evolution, together with some natural basis B prime, and we assume that our algebra A is perfect. Then graphs of algebra A and algebra A prime, they are isomorphic, even if algebras are isomorphic. So it's essentially speaking, it means that if we have one and the same algebra A and we have two different natural bases, so if our algebra is perfect, then these graphs is the same graph, it's the same graph. Okay. And so here our result. So all three-dimensional evolution algebras were recently classified. So here's a classification of simple. I forgot to write down simple. Three-dimensional simple. Well, actually, all three-dimensional evolution algebras were also classified, but here we are interested in classification of simple evolution algebras. So a classification of simple, here I missed the word, algebras consists of 27 families. So it's quite a lot of families, and some families, they have many parameters. So it's really a huge set of algebras. And so we consider the case of zero characteristic. Algebra A is simple evolution algebra of dimension 3 with non-trivial group of automorphism. And then we described algebras of invariants and verify that AP equality holds in this case. Well, it was not necessary to consider all 27 families because using some known results, we were able to show that actually only 8 families have non-trivial automorphism groups of algebras, of evolution algebras in dimension 3. And for these algebras, we also were able to describe first automorphism, groups of automorphisms, and then calculate invariants, and then verify that these invariants are generated by traces. So that is it. And about references. So here's the text about two-dimensional algebras. It's in the archive. It's submitted, but we still don't have any reply from the journal. The second paper, it's about three-dimensional Leibniz algebras. It was accepted to Canadian Mathematical Bulletin. And so it can be find out in archive or on the website of this journal as well. As some preliminary version is available. So that is it. Thank you for attention.
Thank you for a very nice talk, Artem. Are there any questions or comments anyone wants to make? No? Okay, well, can I thank all of today's speakers and everyone who's logged into today's talks, and especially the organizers of today's seminar. And all that remains for me to do is to wish a very happy Christmas to everyone who celebrates it. So thank you for your attention.